Our next section is going to deal with phase changes, and I've kind of set up a diagram here that's similar to figure 1120 on page 439 of your textbook. And let's kind of get some vocabulary down as we talk about these certain phase changes. You're going to be responsible for knowing the terms that we use. So if we go from a solid to a liquid, this is known as melting. And if we go to a liquid to a gas, we refer to this as vaporization. If we go back from a gas down to a liquid, this is called condensation. And if we go from a liquid to a solid, we call this freezing. I think these are very commonly known terms that we typically use very often. Okay? If we go from a solid to a gas, we call this sublimation. And if we go from a gas to a solid, this is referred to as deposition. And in every phase, or with every phase change, we see an accompaniment of energy and a change of energy in that system. And we can look at this by looking at something called a heating curve. And I'm going to give you the example of the heating curve for water. So in a particular heating curve, on the y-axis we have the temperature, which is typically expressed in degrees Celsius. And then on the x-axis, we have the heat added. So we're going to start here around negative 25 degrees Celsius. Then we'll increase up to about 0 degrees Celsius. And then we'll have another benchmark at 100 degrees Celsius. And I think most of you are familiar with water. So the 0 degrees and 100 degrees are the melting and the boiling point for water respectively. So what happens is initially we start at negative 25 degrees Celsius. We have a solid, right? So the water exists as ice, and it increases as we increase the temperature and the heat added. Everything happens, fairly linearly until we hit 0 degrees. And what happens at 0 degrees is that we see that we have to add a pretty decent amount of heat before the temperature will change. Okay, so we add some heat, and then another thing happens between 0 and 100 degrees where we see this linear increase and a direct increase in temperature and the heat added. But then we also see a flat line here where we have to add a lot more heat before the temperature is going to change. And then we see a bump like this. Okay, so at this bottom point right here, below 0 degrees Celsius, our water exists as ice. From 0 to 100 degrees Celsius, it's going to exist as a liquid. And from 100 greater, we're going to see water vapor. So we have solid, liquid, and gaseous phases. But some of the things that we need to investigate here is, why is this line completely flat? And what can we, how do we define this? Okay, so there's energy is going to be needed to overcome the intermolecular forces to change between one phase to another. Okay, and this line right here, when we go from a solid to a liquid, we call this the heat of fusion, or we'll call it the delta H of fusion. Okay, and when we go from a liquid to a gas, this is going to be called the heat of vaporization, or the delta H of vaporization. So we need to kind of define what each of these terms are and kind of relate them to the little aspects of this heating curve. Okay, so the first is fusion, which is commonly referred to as melting. And this happens when we go from a solid to a liquid. And in order for this to happen, we need to add heat. So this is an endothermic process. Okay? So as we increase our temperature, we are going to increase the kinetic energy of all of these particles. And we're going to increase the kinetic energy until the kinetic energy is roughly equal to the intermolecular forces in our particular species here. So once we have enough energy to overtake the intermolecular forces, we're going to change that phase. Okay? And we refer to this as the delta H of fusion in terms of the energy here. So this is referred to as the molar heat of fusion, and it's typically represented in kilojoules per mole, and it's the heat required to melt 1 mole of a solid. Okay, so we use this delta H of fusion. Remember that when we talk about these energy quantities, that they're going to depend on the amount, right? So we refer to this as the molar heat of fusion, which is the heat required to melt 1 mole of a solid. Okay. In addition, we have vaporization, which is also referred to as evaporation. And this is when we have a liquid going to a gas. Again, we need heat in order to do this, and this is also an endothermic process. Okay? So, in order for a particular molecule to evaporate, it must have sufficient energy to overcome the intermolecular forces, just like we talked about before here, right? And these need to be near the surface because these molecules need to escape into the next phase, in this case a liquid to a gas. So again, we're adding heat, we're increasing the temperature, which is going to help these particles escape the surface. And our delta H of vaporization is referred to as the molar heat of vaporization. And again, this is in units of kilojoules per mole. And this is the heat required to convert 1 mole of liquid to vapor at a given temperature. And in both cases, the takeaway message that we can take from these two quantities is that as we increase the delta H of vaporization, okay, if we see an increase of the delta H of vaporization, we're going to have stronger intermolecular forces in the liquid. And as we see an increase of the delta H of fusion, we see stronger intermolecular forces in the solid. And these are some pretty good take-home messages to take away from here. Number one, we have to also recognize that the intermolecular forces play a large role in this. Okay, and the heating curves are going to change for each species depending on how their intermolecular forces are. Okay, so we need to be able to recognize the intermolecular forces, and we're going to see an increase in the delta H of vaporization and the delta H of fusion based on how strong our intermolecular forces are. So the stronger the intermolecular forces, the higher values of delta H we're going to see for each of these, and the more energy it's going to be required to change each of these phases.